up a substance, what do you think you would be making up? A solid, a liquid, or a gas?
Liquid?
Let's say you're like an atom or molecule, and then he's another one, and you're another one, and he's another one. What do you think, given the state of affairs in this room right now? Are you guys a solid, a liquid, or a gas?
Solid.
A solid. You have equilibrium positions. Like you're on that chair, and you're moving, right? You're going like this, right? It's like the jiggling. And you go like this, and you right, and you look this way. But overall, you're in that space, right? And same him, same for you, same for him, right? So it's like you have equilibrium positions, right? When class ends and you get up and you start moving, what do you think you're representing? A liquid. Now you're flowing. Now you're there, but then you don't have like in water, like this is not always there. You know, this one it flows, right? It can move. So you get up here. You may ask me a question. You may go over there. You talk to someone else. Walk out, right? And we're pretty much roughly about the same distance away from one another. Although we're gonna get crowded over here because the way out is that way. What would happen if, for example, I don't know, well, I don't want to even think about it, but we have to run out of this room immediately. Then we'll be like making up a gas, right? They say, we're moving fast, and you get the idea, right? I hope you get the idea. Okay, so linear expansion. So I have these two expressions here for linear expansion and another one for volume expansion. So for linear expansion, if you consider, this is good for like wires, very long, like a wire. Also liquids like a mercury thermometer, right? So let's say this is like a wire, right? And the temperature is T sub 0 at some instant. So initial temperature is T sub 0, and the length of it is L sub 0. So you got this wire, it's got this length, and its temperature, right? And let's say it's thin. Now, what happens as you raise the temperature of the wire? What happens is that, the atoms jiggle more, and they kind of need more room to jiggle, and so the solid as a whole expands. And if you raise the temperature by delta T, because now the new temperature is what it was before plus the addition, right? Then what will happen is that the wire, for example, is going to get longer. And by how much is it going to increase in length? What will be delta L? We know what L initial was, but by how much will it increase in length when it increases in temperature by delta T? And that's what this formula tells you. So this formula tells you the length by which the wire will stretch when you heat it up by a temperature change of delta T. Notice that how much it will stretch, get longer, depends on how long it was to start with. It depends on L sub 0. So if I have, for example, this marker, and this other, let's say this is just one marker. And, they're made up of the same material. The alpha that you see in here, it's a measure of the intermolecular forces. It's a measure of, it's a parameter that depends on the type of material this is, the type of wire this is, if this is iron, if this is nickel, if this is aluminum, if this is copper, if this is, So the parameter alpha here has to do with the type of material. So there should be a table in the chapter 17 of the textbook with values of this parameter alpha for the various materials, right? What would happen if we have the same material, so described by the same parameter alpha, the same initial temperature, and I raise the temperature of both of these to the same final temperature, so they're both going to increase in length. So are they both going to increase by the same length, delta L, or no?
No.
No. Which one is going to increase more?
The longer one.
The longer one. Yes? The longer it is to start with, the longer it's going to get for the same change in temperature from the same initial temperature to the same final temperature, same material. Right? The Golden Gate Bridge, for example, in San Francisco, like these days, summer, it's hot, it's getting hot in San Francisco. I understand like September is one of the hottest days, and we're just getting there, and wow, this week it's hot. It's gonna be hot. So the Golden Gate Bridge increases in length by as much as a meter. This used to be like a meter, by this much, from winter to summer. That means that when the bridge was built and you build them in sections and so on, you need to allow for the expansion of of the chunks that makes up the bridge. That's what these things are for, right? Expansion slots. So imagine if they build one segment and it's like this, and then right next to it they put another one, and suppose they happen to pour the concrete and so on in January or February when it was cold, right? Then what happens when the summer comes along and the thing expands because it gets hotter, right? Then if there's no room for that expansion, it'll just buckle. And then there are more chances of an accident, someone losing control of a car and so on. And so to allow for that expansion, right? So they make them like this so that they're like that. So that if this segment expands in this one, they kind of go into one another like this without buckling. And then when it gets colder in the winter time, they'll pull out. Summertime it gets hot, like this. And so you allow for that thermal expansion effects, right, from winter to summer, and summer to, and even when you walk outside this building, you have this path, right, to the library, so on to the planetarium. You get this, you see this concrete over here, and you have grass over here, and grass over there, or maybe dirt. Right now they have some dirt over there next to the planetarium, so with some boulders. Have you seen that? I was told that the biggest boulder that they have over there now is around 6,000 pounds. But anyway, that's off the topic. So you have this chunk of concrete, and you have grass. Let's say you have grass over there, and if you look at them, they're like squares, right? But this groove, this space between them. Why do you think they have that space? Don't think that it's for the ants to get from this side to that side without getting stepped on by the students. No, it's to allow for that expansion, right? So that they can, this one can expand that way, this way, but then they can also go this way, and you don't want them to buckle because then someone can trip as they walk on the. Okay, so that's that. And things get longer in one dimension. What if you have an object like in some three-dimensional object, some solid, right? Then it'll increase in length along the x-axis, along the y-axis, along the z-axis. So overall, the volume is going to change. And so this is the formula that tells you what the change in volume is. Again, it depends on how big it was to start with. So what is the change in the volume of the object when you raise the temperature by delta T? When the initial temperature was V naught. When the initial volume was V naught. And then beta, again, is a parameter that has to do with the type of material that you're considering. And by the way, this beta here, this is called the thermal coefficient of volume expansion. Is roughly, depending on the type of material, is roughly 3 times alpha. Alpha, which is the thermal coefficient of linear expansion, is like it takes into account expansion along one dimension. But when an object changes volume, it usually changes volume in 3 dimensions, like it goes this way, and that way. And so beta is like this alpha plus this alpha and this alpha. These alphas, but if the expansions are the same along the 3, different directions, then beta will roughly be equal to 3 times alpha. And that's one of the homework problems that we have. To show that beta is equal to 3 times alpha. So if you look up, for example, there should be a table in chapter 17. I think I didn't include it in my notes, but there should be a table in chapter 17 with values of alpha for some materials and beta for some other materials, and then there may be some materials which have a value for alpha and a value of beta, and then you'll see that beta is roughly 3 times alpha. And I said roughly because some objects are more easily stretched along one dimension than another dimension, right? And so the alpha is not necessarily the same for all dimensions. What else? Notice again that both of these formulas for the change in length and for the change in volume, right, they both involve just a delta T. So the temperature difference in Kelvin is what you need. Also, if this means that if I raise the temperature of a substance, right, of some object, this is by how much the volume will increase. On the other hand, what happens if I decrease the temperature by delta T? What's going to happen to the volume? It will shrink, right? So this is the volume by which it will shrink. Not the final volume that it's going to have, but by how much it's going to change from the initial to the final, right? So it's the change in the volume. That delta V is not the final volume, it is not the initial volume, it's that by how much it's going to change. It's a result of the temperature having changed by delta T. So, volume expansion. As far as volume expansion, this is actually something that I do quite a lot at home. You buy, let's say, a glass jar with, I don't know, jelly inside or something, and then the lid is metal. And you bought it, and it's brand new, and you try to open it, and can you open this up? And it's like, you try it, and you can't, and you dry your hands, and you can't. So you eat some spinach like Popeye, and you throw yourself on the floor, do a few push-ups, get strong. Okay, I'm gonna try again. Maybe, maybe not. Right? Well, what if you put it under hot running water? So the hot running water is gonna raise the temperature of the metal lid, which has a specific value of alpha, and that's in contact with the glass, which has a different value of alpha. So the coefficient of thermal expansion for metal is higher than the coefficient of thermal expansion for the glass. So as you raise the temperature of both of them, slightly, all you need is to raise it enough so that the metal expands a little more, and that helps loosen it than the glass, right? And then with your strength, boom, then you can open it. And when I do this at home, I don't do that for more than half a minute. It's enough, as long as the water is hot. You need to be there like an hour, okay, so that yes.
Is part of the metal having a higher alpha coefficient just because it's a better conductor of heat, so it just conducts more of that energy to it rather than the glass?
And
that's
also
why
it has to do with the intermolecular forces between the atoms that make up the metal. Yeah, it's like they receive the energy. Yeah, they spread it out more readily also, but then every piece of that glass is in contact with that metal also, right? So the thermal energy is going to get to the glass, but it's like the metal atoms are holding one another not as strongly as the atoms in the glass. And so they stretch a little bit more, and all you need is to just a little help, right? And then with your strength, you can still open it, yeah. But it's something that, it's, anyway. Okay, so, I want to talk about this here. When you look at these formulas here, this one, let's say this one, change in volume is the initial volume multiplied by some parameter that depends on the type of material, and then the change in temperature. What happens when you raise the temperature? And I just said that a little while ago. What happens if you raise the temperature of the object? Does the object therefore expand or shrink?
Expands.
It expands. And what happens if you lower the temperature?
It shrinks.
It shrinks. Good? Okay, there are exceptions to that rule. There are cases when you raise the temperature of something and you expect it to expand, but it does the opposite. It shrinks. Or you lower the temperature and you expect it to shrink and it expands. And one substance that has that behavior, anomalous behavior, weird behavior, anomalous behavior is water. But water has this anomalous behavior only in a certain temperature range. And that temperature range happens to be from 0 degrees Celsius to 4 degrees Celsius. So from 0 to 4 degrees Celsius, water does the opposite of what you would expect it to do when you heat it up. You expect it to expand, it shrinks. Or when you cool it down, you expect it to shrink, it expands in that temperature range. Okay, so, and this has some interesting consequences, very important consequences. This anomalous behavior of water. So what if I draw a graph of temperature on the horizontal axis? Let's say I'm going to use degrees Celsius and density in kilograms per cubic meter, and the substance that I'll consider is H2O, water. And I'm going to label this 0, 1, 2, 3, 4, 5, 6. That's enough. Okay? Okay. How about we consider a chunk of water at 6 degrees Celsius. And the density is whatever, I don't care, some number. I just put a dot above 6. Whatever the density is, it doesn't matter right now. Okay? Remember that density is mass over volume, right? It's the mass of the object in kilograms divided by the volume occupied by the object in cubic meters. Now, what would happen, right, if I cool down this water from 6 to 5 degrees Celsius? So I cooled it down. Does it expand? Does the water expand? Or does the water shrink? Shrink. What's the temperature range where water is weird?
0 to 4.
0 to 4, right? So 6 to 5, we're outside that range, right? So this is the anomalous behavior over here. So if it shrinks, if the volume gets smaller, what's going to happen to the density? Is it going to get bigger or smaller?
Bigger.
Bigger, right? Because you're divided by a smaller volume, by a smaller denominator. So the density is going to get bigger, right? I'm just going to put it over here. I don't care how much bigger, that's besides the point. What if you continue to cool down this water, this body of water, from 5 degrees Celsius to 4 degrees Celsius? Will it shrink or expand?
It would shrink.
It'll shrink, right? It does what you expect it to do. So, and if it shrinks, if the volume gets smaller, the whole quantity, the density is going to get bigger. So it's going to go up to here. Right? That's supposed to be above the 4. What happens when I further cool down the water from 4 degrees Celsius to 3 degrees Celsius? What do I expect it to do?
Shrink.
Shrink. But what does it do?
It grows.
It expands.
Oh.
And if it expands, what happens to the density? If you divide by a bigger denominator, it's going to get smaller. So then what's going to happen is the density is going to go down to like here. And what happens when it goes from when it cools down from 3 to 2 degrees Celsius?
It's smaller.
You expect it to shrink, but it expands. And if it expands, the density goes down. Yes? Did I say it wrong?
Can you repeat that?
You look unhappy.
No, can you repeat it?
I said it too quickly.
Yeah.
So, as it cools from 3 degrees Celsius to 2 degrees Celsius, you're cooling it down. You expect it to shrink,
But it expands.
but it does the opposite, so it expands. But if it expands, what happens to the density?
It decreases.
Decreases. So I'm going to put it smaller over here. And the same thing when I cool down the water from 2 to 1. You expect it to cool down, to shrink, but it expands, and if it expands, the density goes down, right? Just keep doing this until I get there, right? This is the anomalous behavior of water. It's like beta is negative or something like that. So, looking at this graph, let's say I connect these points. At what temperature does water have the highest density? At 4 degrees Celsius. And sometimes, people take entrance exams to medical school, called the MCAT, and they'll hit them with this question. What temperature does water have the highest density? And it's not something you can work out. Either you know it or you don't. It's one of those things that either you know it or you don't. It's not something that, let me work it out. I got 4 degrees. You know it or you don't, right? So 4 degrees Celsius. Maybe I'll put this here. That's a bad fit, right? Okay. Now, it turns out that this is 1,000 in these units. Now, when it reaches 0 degrees, it's like 999 point something. I gotta look it up, but it's like ridiculously close to 1,000. And we're talking about pure water. It's like 999 point. What is this? It would be like 999.89. Is that right? That's 8.8. And there's a break over here, obviously. It's like, yeah, there's a break, right? And then, what happens if you further cool down this water and you remove thermal energy from it so that it crystallizes into ice? Then, it turns into ice with these voids between the molecules, right? These open hexagonal structures, and the density really drops, right? And so the density drops to, like, in that case, I don't remember, somehow 920 rings a bell. And, therefore the density of ice is, you might want to look that up to double check, but smaller than 1,000. And then the ice floats on the water. Now, this weird behavior of water, this anomalous behavior of water, can be used to explain the following. Not that. Okay. So let me tell you about something cute that happens. Consider a lake and the onset of winter. Let's say in Alaska or Canada, something where it gets cold. So here's this lake, right? And you got water in it. So this is air, and this is water. And we'll put a little cute fish over here. It's supposed to be cute, but some plants. Okay? And the temperature outside is, let's say, 6 degrees Celsius. It's getting colder, 6 degrees Celsius outside. So what's gonna happen? This air is in contact with this water on the surface. It'll cool the water to 6 degrees Celsius. And let's just start with the whole, you'll see why. The whole water is at 6 degrees Celsius. Let's just start with that. You'll see why later on why that would be the case. And by the way, when I say 6 degrees Celsius over here, I don't mean in this corner. I don't know what the temperature is over there. You know, this is at the bottom of the lake. This is at the top of the lake, right? Now, you know, it's getting colder outside on average, right? So let's say the temperature drops to 5 degrees Celsius. So then that air at 5 degrees Celsius is in thermal contact with the water on the surface, so it's going to cool it down to 5. It's going to cool it down to 5 degrees Celsius. Now, the water at the bottom here is not in thermal contact with that, right? So water is not a good conductor of thermal energy. This is a clean lake. Now, which of these two waters, the water at the top of the lake at 5 degrees Celsius, or the water at the bottom of the lake at 6 degrees Celsius has a higher density?
Can you repeat that again?
Which of these two waters is denser?
The water at the top of the lake.
Look at the graph.
5 degrees.
Which one?
5 degrees Celsius?
Which is the one on the surface, right?
Yes.
So therefore, what's going to happen?
It's gonna sink.
It's going to sink. But it's not going to leave a hole up there, right? It's going to get replaced. So the less dense water will rise, and the denser water will sink. So you have these convection currents like this. And then what happens when this 6 degree water gets up here? It'll get cooled by the air, become, you know, water at 5 degrees Celsius, sink. More water will go up at 6 degrees, cool down until the whole thing is at 5. And you see that's why I started like this. You know, continues to get cold outside, on average, 4 degrees Celsius. So then that water, that air, I'm sorry, I keep calling it water, that air, that'll remind me, that air will interact with this water and cool it down to 4 degrees Celsius, right? But all the while, you have water at 5 degrees Celsius down below. Which of these two waters is denser? The one on the surface or the one at the bottom of the lake? The one on the surface. And therefore, that water is going to sink and it'll get replaced by that. And then, as this water reaches up here, it'll cool down to 4, and then it'll sink, and then more water at 5 is going to go up, cool down to 4, sink because it's denser, and blah, 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 until this reaches 4 degrees Celsius. Keeps getting colder outside, 3 degrees Celsius. So that air is going to interact with this water and cool it down to 3 degrees Celsius, but you have 4 degree water down below. Now, which of those two waters is denser? The one on the surface of the lake at 3 degrees Celsius or the one at the bottom of the lake at 4 degrees Celsius? Therefore,
The top of the lake will freeze.
it's just going to stay there, right? So you're not going to have convection currents. And the other one, less dense, the 3 degree water will float on the water at the bottom of the lake. So it keeps getting colder outside. 2 degrees Celsius, 2 degrees Celsius. Well, you still have this water at 4 degrees Celsius over here. Water is not a good conductor of thermal energy. If you don't have those convection currents, and it's a big lake too, right? So, and then it keeps getting cold outside, 1 degree Celsius, 1 degree Celsius, and then you got water 4 degrees Celsius, less dense, keeps getting cold outside. 0 degrees Celsius, 0 degrees Celsius, 4 degrees Celsius, right? If it gets getting colder outside, then where will the water freeze? Or begin to freeze? At the top of the lake. And so it keeps getting colder outside at -1 degree Celsius and so on, then you begin to build this layer of ice. You know, this is the ice. And by the way, ice is an even worse conductor of thermal energy than the water, so it really serves to really shield this water here from the very harsh cold air outside. And all of this, in other words, why do lakes freeze from the top to the bottom? Not throughout, but from the top to the bottom. Because of this weird behavior of water. And guess who's really, really happy about water behaving anomalously like this? Marine life. They don't have to get reinvented every spring. Professor at UC Irvine, professor of physics, Steve Barwick, he conducts experiments detecting neutrinos, and they conduct experiments in the South Pole. And in the South Pole, this, it's a sheet of ice. The South Pole, this is like 4 kilometers thick or something. And then they put instruments in there to pick up neutrinos and so on. This is like 4 kilometers thick, but then you have water underneath that. So, but at any rate, because of this behavior, what I've seen explained as, what's the physics behind this. So apparently what happens is that when the water reaches 4 degrees Celsius, you begin to have microscopic pieces of ice beginning to form, which is microscopic. It's still like water to you and I when you see it and so on. And those microscopic pieces of ice beginning to show up, kind of lower the density a little bit and lower, and then, but then over here, there's like boom, then it, when it reaches 0 degrees Celsius and then you keep removing energy, then it's like, whoa, the crystallization into ice is more macroscopic, and then it drops. Did anyone check the density of ice? No, I'm just curious now that somewhere around there it rings a bell.
Should be 917.
17. Oh, okay, cool. That's good enough for me. Good. Thank you, sir.